By the way, a related note on this, you can start thinking, this is a very simple scheme we came up with, which is just the Euler scheme. You can think about more generic schemes to say, look, if I want to have a one-step scheme into the future, so I take my solution now and let's say I get my solution later, right? Then the question is, well, how do I think about modeling this? Well, same thing is going to happen over here. If you take n steps, you're going to get a to the n y0. Then it's really important what happens to this matrix A of n. Now, one of the linear algebra tricks that you may have learned, hopefully you did, but we'll kick it around right now, because when I learned it, it was like, oh, cool trick. That's not so useful. We never used it. It just seemed like, here's a trick. And then that's it. But here's a trick, and you can actually use it, which is to say, if you have this matrix, and this is for a matrix exponentiation, one way to do this is to multiply this matrix n times when n is huge. So you're going to do huge amounts of computation to get this. The other option is to say, well, you know what I can do with a matrix? I can diagonalize it. And here is the formula for this. And it doesn't really matter if you remember this or not. There's just this trick that says you can take a matrix and you can rewrite it as 3 matrices. Awesome trick, right? Seems like I did more work. S is the matrix of eigenvectors. S inverse is its inverse. And this lambda matrix is a matrix which is diagonal, which has all the eigenvalues on the diagonal. It's a diagonal matrix. S was the matrix of eigenvectors. But the important thing is this diagonal matrix. And when I start doing multiplications of these things, let's say a squared, it's this times itself, what happens to the s and s minus 1 when they interact? The inverses, they give you 1. Awesome. They kind of cancel out. So if you do it n times, what you end up with is the following. So you say, well, I still have a problem. I have still this matrix that I'm lifting to the nth power. Yes, but this matrix is now diagonal. And if you lift it to the nth power, take this matrix, lift it to the nth power, all you got to do then is just do that. Easy. Okay. What matters now then is the following. I have this object, I have this power to the nth power, and all I care about is, look, I'm lifting every one of these eigenvalues to some n, which is going to infinity. So you ask, do any of these blow up? So what's the condition on the lambda i's? You know, so if your lambda I is bigger than 1, what happens if you take a number bigger than 1 and you raise it to the infinity power? It becomes infinity. Unstable, right? So that's how you do a classification of the scheme in a more general way. It's the same thing we just did, but now it's all related to the eigenvalues of your matrix that tells you how to go from step A to step B. Okay. All right, so fine. A couple more thoughts here. Yes? We're not dealing with relative error. So when you talk about stability of iteration schemes, all you really care about is does the error grow, not whether the relative error grows. Because in this case here, you could start saying, well, what about relative error? What's going on with that? Okay, your error does go to infinity. So even if you have a very large number, you're going to still add to it another huge number. Now you can say it's relative because it's got a huge number, but when you just go to classification of is the scheme stable or not, all that matters is what's happening to the error in general. And does the error grow to infinity? And then you avoid schemes that do that. Okay. Okay. So let's do one other thing here. I'm going to contrast what we have here with the Euler method. And let's go back to do this now with, remember we had this differential equation that I just erased? Okay. And here's the thing we're going to do. Euler said, or this was what's called forward Euler. The solution in the future is what it is now plus a little bit of something, and it's delta t times this function f evaluated at y of n. That's forward Euler. Backward Euler, which I talked about just at the end, is, well, let me evaluate this at the future point instead. Okay? And again, I made this point, which was, wait a minute, the future is what it is now plus a little bit of the future. But I didn't know the future. So how am I going to solve this thing? So then that's the implicit thing. And so in this case, it's actually easy because it's such a easy differential equation. What I'm going to do is put in the f. And instead of, it's just going to be, remember I'm solving this here. So it's going to be lambda. I'll just do 1D. There it is. Now, again, I can move this to the other side, pull out the y of n plus 1, and what I can find is y of n plus 1 is equal to 1 over 1 minus lambda delta t y of n. Look at the difference in this scheme. So if I take n steps in this thing, then what I'm going to actually do is take this thing to the nth power, make that y0, make that n. So you hear all the voices outside the door. This is what happens first week. Everybody's uber excited. They can't control themselves from coming 10 minutes early to class, right? And like walking in the door 10 minutes before class. It's not even that crowded of a class. Watch what happens. I guarantee you by the middle of next week, you won't hear them until you're gone. You'll be gone by the time they start making noises. Here's your formula. Now contrast this. This is just the same differential equation using forward Euler to using something that backward Euler had this thing in it. So you could still do stability criteria. Here's the stability criteria that you had for forward Euler and backward Euler. And for this one here, let's let z, for instance, be... actually, let's do the following. What you care about is this, does this thing blow up? If this thing, so now you have a divide by here. And let me do the following here. I'm going to erase here. And what I'm going to do for both these schemes, I'm going to let z be some number, lambda delta t. That's what you see everywhere. And for forward Euler, right, what we have is this thing blows up if 1 plus z absolute value is greater than 1. For backward Euler, this thing blows up if this is greater than 1. So let me draw you two pictures. This will be forward Euler. This will be backward Euler. I asked the following question. These are the criteria of when things, I shouldn't be stepping in these regions. These regions make the scheme unstable. So let me ask, where can I step and have stability or instability? So for the Euler, here it is. And it turns out this is what it looks like. In here, this is a ball of radius 1. That's stable. Everything else is unstable. So that's how that works. A little area where you can step in and forward Euler will work. Over here, here's the criteria. Here's what's unstable. Everything else is stable. Now I made this comment about people like implicit schemes because they give you great stability properties. If you can't see it from here, it's a problem. So let's just make sure you understand this figure. This figure says the following. Okay? If I'm stepping using backward Euler, all I got to do is avoid this little region. I can take a step anywhere else I want. This is like being out, well, okay. Normally, if you're going for a walk in a park, maybe you're just trying to avoid a pile while you're walking. It's the only thing you got to do. This is more like walking near the fountain here with all those geese. Because everywhere you walk, it's bad, except for very small regions. Okay? So now if you were going to write a scheme to walk through a nice meandering differential equation park, you would want to be in this park and not that one.